Hello friends. Let us discuss next topic, that is intrinsic and thermal breakdown. These two topics are different, like intrinsic breakdown and thermal breakdown are the two different topics which we had to study in this lecture. So what we have in intrinsic breakdown, that is going to be studied first. So in intrinsic breakdown, when voltages are applied only for a short duration of the order of 10 raised to power minus 8 second, the dielectric strength of a solid dielectric increases very rapidly to an upper limit called as intrinsic breakdown. So this is nothing but the intrinsic electric strength of the solid insulating medium. So exactly what happens? Whenever a solid specimen, let us consider this is the specimen which is insulated on some of the conducting medium, and when the current passes through this medium for very small time due to the application of voltage, that current heats up the material. That current heats up the material or heats up the specimen. And basically what happens, that specimen, due to heating, the width of it reduces little bit, or we can say that that specimen becomes compact. This reduction of the size of that specimen is very less, it is very small. But when all the molecules which are present in that insulating medium get compact, we call that as a strength of the material. So this intrinsic electric strength get increased. Experimentally, this highest dielectric strength can be obtained only under the best experimental conditions, when all extraneous influences have been isolated and the value depends only on the structure of the material and the temperature. We get that condition. The maximum strength range from 5 megavolt per centimeter to 10 megavolt per centimeter. For an example, if we have a polyvinyl alcohol, this has a dielectric strength of 15 megavolt per centimeter at 196 degree centigrade. So the maximum electrical strength which is recorded for this particular solid medium is 15 megavolt per centimeter. In intrinsic breakdown, which depends upon the presence of free electrons. So whenever a solid insulating medium, so I just call this as dielectric specimen. This dielectric specimen has certain free electrons which are capable of migration through the lattice of this dielectric. So this is nothing but the lattice of the dielectric. A small number of conduction electrons are present in this specimen or in the lattice, along with some structural imperfections. So there may be some structural imperfections, and that imperfections is more than enough to have the formation of new electrons. Even these imperfections and the impurities which are present in the dielectric specimen or in the lattice develops the more number of electrons. So the impurity, atoms or molecules or both, act as a traps for the conduction of electrons. So that impurity, if that there is an impurity present in any of the lattice, then that acts as a trap. so that electrons get locked in that particular space. So that traps the electrons, and the electric field which is present with the temperature can increase the electrons. So when these ranges are exceeded, when the electric field and temperature range get exceeded, additional electrons are released. Additional electrons are released. And these electrons participate in the conduction process. So whatever the electrons which are released, that participate in the conduction process. So based on this principle, there are two types of intrinsic breakdown mechanisms have been proposed. The first is called as electronic and another is called as streamer breakdown. So in this intrinsic, there are two mechanisms explained to get the understanding of the participation of the electrons with the conduction electron to have or to study the breakdown process. So let us start with the first. In electronic breakdown, as we already mentioned earlier, the intrinsic breakdown occurs in the time of the order of 10 to the power minus 8 second. So this is assumed to be the electronic in nature. The initial density of the conduction electrons, the initial conduction electrons, that is called as free electrons. Free electrons are assumed to be large. So more number of large electrons, free electrons are present in that specimen. And electron to electron collisions which occurs in the electric field when that electric field is applied gains the energy. So those electrons which are get collide develops, it is due to the energy gain during the electric field application. So that electrons which gains that energy cross the forbidden energy gap, that it jumps from the valence band to the conduction band. Now the repetition of this process, that is what is that process is the density of the electrons which are already large, and this collision which takes place, that more number of collisions of electrons with electrons releases more number of electrons from it, and this release of those more number of electrons with the heat avails more and more electrons in conduction band. So now the amount or the number of electrons in the conduction band becomes more, due to which the gap between the electrodes becomes the conducting gap, and eventually that leads to the breakdown. So this is our first breakdown called as electronic breakdown. In this electronic breakdown, we are considering the number of electrons which are present or free electrons which are present in the lattice are more, and the collision gives us the formation of the conduction and hence the breakdown. Now, another process is called as streamer. In intrinsic is streamer breakdown. That streamer breakdown, it is similar to the streamer breakdown in the gases. So this streamer is nothing but the cumulative ionization. This is nothing but the cumulative ionization. So conduction electrons which gains the sufficient energy, conduction electrons which gains the sufficient energy from electric field, that is application of electric field from which that electrons gains the energy, liberates more number of electrons from the lattice, and that takes place due to the collision process. So when this conduction electrons gain sufficient energy above a certain critical electric field and cause the liberation of electrons from that lattice atoms by collision. Now under uniform field conditions, if the electrodes are embedded in the specimen, if the electrons are embedded in the specimen. So I'm just considering this simple example where we have a cathode and anode electrode. And just in between that, we do have the lattice which is present, and that lattice is present in between the electric field. There is an electron which is present here. That electron is shown with this blue circle. So if the electrodes are embedded in the specimen, breakdown will occur when an electron avalanche bridges the electrode gap, that is gap of the cathode and anode. So an electron with the dielectric, an electron which we are considering here within the dielectric starting from the cathode. So it starts from the cathode and will drift towards the anode. And during this motion gains the energy from the electric field. So these lines are representing the electric field which is present between the two electrodes. When this electron gains the energy and loses it during the collision, when it collides with the neutral molecule or the other electrons which are present in that lattice. So when the energy gained by an electron exits, when energy gained by an electron exits the lattice ionization potential, energy gained is greater than the lattice ionization potential, an additional electron will be liberated, that is released due to collision of the first electron, due to the first electron collision. This process repeats itself. So whatever the process I have mentioned here, that particular process repeats itself. So like the conduction electrons gains the energy, liberate mu number of electrons in the lattice, that electron avalanche bridges the gap, that avalanche bridges the gap and the breakdown occurs. So this dielectric electron starts from the cathode, reach to the anode, and it gains the energy and loses its energy during collision. So this process continues, and that is responsible for the formation of the breakdown. So this repetition gives us the breakdown. And remember one point here, that single avalanche cannot create or is not responsible for the formation of the breakdown. So here I have just considered simple example where I do have a electrode which is shown here. There is a specimen which is represented in circle. So this is that specimen lattice. This lattice is having different layers on which there is a formation of a tree, which we have studied earlier. So it continues. There may be the break of that tree somewhere at one point, but few points reaches to the other, and slowly that process continues. So avalanche exceeds that critical size, and due to which the breakdown occurs, the breakdown takes place. So as I said, the single avalanche cannot do so. There is a step-by-step process through which the entire thickness of the material. So if I just call, there is a thickness T. So entire thickness of the material, which is shown in this figure, that finds the breakdown. So this can be readily demonstrated in the laboratory by applying some impulse voltage between point plane electrode. So over here, the electrode which I am considering is point plane electrode. This point plane electrode through which we are applying certain voltage to it, and therefore we are getting the formation of the breakdown. So this is all about the intrinsic breakdown, which is classified into two types as intrinsic breakdown and the avalanche or streamer breakdown. That is electronic breakdown and streamer breakdown. Now let us understand next breakdown process called as thermal breakdown process. In general, the breakdown voltage of a solid dielectric. So the solid dielectric, again, we are considering this breakdown voltage of a solid dielectric should increase with its thickness. So it means this voltage is directly proportional to the thickness. But this is true only up to a certain thickness, up to certain thickness, above which the heat generated in the dielectric heat generated is due to the flow of current is due to the flow of current. This flow of current determines the conduction, that gives us the conduction. So when an electric field is applied to a dielectric, so whenever a electric field is applied, so let us consider this is your electric field and there is a specimen placed in that electric field. So when the electric field is applied to a dielectric, conduction current, that may be a small, flows through the material. So whatever the material we have, through which we get the conduction current. This conduction current helps to heat up the specimen and therefore the temperature increases. Because of the flow of current and the electrons collision, the heat generated in the material, so therefore it heats up the specimen and the temperature increases. So the heat generated is transferred to the surrounding medium. So this way we are getting the heat generation, that is current passes through, that is conduction current passes through the specimen, nothing but the electrons. When that electron collide with the another electron, that collision develops definitely the new electrons, but at the same time a heat. So rise in temperature, rise in heat basically gives us the heat generation. This heat generated is transferred. Heat generated is transferred to the surrounding medium by conduction. As we know from the physics, the conduction, through conduction, that heat is transferred, and by radiation. So in conduction through the solid dielectric and by radiation from its outer surface. So if we have this specimen from outer surface, the heat is transferred, and from inside through conduction, the heat is transferred throughout this specimen, so that this complete specimen get heat up. The equilibrium is reached. The equilibrium is reached when heat rise, the temperature of the dielectric plus the heat radiated out, which is equal to the heat generated. The heat generated under DC stress is given by WDC is equal to E square sigma watt per centimeter cube, where sigma is DC conductivity. Heat generated in AC, that is heat generated in AC, is given by E square into F into epsilon R tan delta upon 1.8 into 10 raised to power 12. This is again watt per centimeter cube. These are the two equations for the heat generation under DC and AC voltage, where F be the frequency, delta be the loss angle, and E be the RMS value of the electric field. Now, there is a heat dissipation, and that heat dissipation is given by the equation WT is equal to CV dt by dt plus divergent K gradient T, where CV is the specific heat, where CV is specific heat. So I just write it here, where CV is specific heat. T be the temperature, capital T be the temperature of specimen. K be the thermal conductivity. I just mentioned here. K be the thermal conductivity, and T, small t, with the time over which the heat is dissipated. The equilibrium is reached when this heat generated either due to DC or AC is equal to heat dissipated. So whatever the heat is generated during this current movement, that get dissipated in the specimen, we call it as the equilibrium condition. But if the heat generated maybe due to DC or AC exceeds the heat dissipation, that is WT, the breakdown occurs. That gives the breakdown. So the thermal instability condition can be represented in this waveform, where on y-axis we have a heat generated or heat lost. This heat lost is shown with a straight line, where this is what the TD. And the temperature is considered on x-axis. So if you consider the waveform, if we consider the waveform for two different electric fields, that is heat generated at different fields, E1 and E2, I get for E1, I get this kind of waveform, and for E2, I get the other kind of waveform which is shown in here. So this is what the heat generated for two fields. Heat generated for two different fields. If I just plot these 2 points where E2 cuts the heat loss on x-axis, I get two different temperatures. Let one temperature is TA and other temperature is TB. So TA and TB be the temperatures at field E2 where the breakdown occurs. So in the temperature region of TA and TB, heat generated is less than the heat lost for the field E2, and hence the breakdown will not occur. So I am repeating myself here, like here the heat lost is shown by the straight line, which I have already said, while the heat generated at fields E1 and E2 are shown by separate curves. So these are the curves which are showing that. At field E2, breakdown occurs both at a temperatures TA and TB. In the temperature region of TA and TB, that is in between this region of TA and TB, heat generated is less than the heat lost. So this is your heat generated. This is that heat generated. So this region is showing that heat generated, and this heat generated is less than the heat lost. So for this region, there is no chance of getting any breakdown. But at these 2 points of TA and TB, the heat lost is less than the heat generated, and therefore there is a chance of getting the breakdown. So this is all about the thermal breakdown. Now, few more points which I want to mention here is the great importance to the engineers is given, as most of the insulation failures takes place in high voltage power apparatus due to the thermal breakdown. So insulation fails because of the increasing temperature of the insulating medium. Thermal breakdown sets up an upper limit for increasing the breakdown voltage when the thickness of the insulation is increased. So here we have already said that VBD is directly proportional to the thickness. For a given loss angle and applied stress, the heat generated is directly proportional to the frequency. The equation already says that heat generated is directly proportional to the frequency, and hence the thermal breakdown is more serious. The thermal breakdown is more serious at high frequencies. As per standards, we have 50 hertz of frequency, but if the frequency increases, then the increase in temperature takes place rapidly. So the chances of getting the thermal breakdown is more serious at high frequencies. The power loss under AC field is higher. The heat generation is also high. As that heat generation is high, the power loss is also high. But in case of AC, it is higher. And hence, the thermal breakdown stresses are lower under AC conditions than under DC conditions. For an example, the maximum thermal breakdown stress for mica, for DC, it is 24 megavolt per centimeter. For AC, it is 7.1. For another rock salt, the maximum thermal breakdown stress is 38 megavolt per centimeter. For AC, it is 1.4. So that's all with this thermal breakdown phenomenon, which we have studied here. Hope you understood this concept of the breakdown of due to thermal formation or thermal mechanism. So thank you so much, guys. Take care.